Okay, let's look at this type of example. Determine all values of x at which the function is discontinuous. At each number where f is discontinuous, state the condition or conditions for continuity that are violated. And again, these are the conditions for continuity. It's based on the definition of continuity of a function, okay? So this is condition 1, this is condition 2, and this is condition number 3. All right, so what we can do in this situation, because it's a rational function, is let's see if it's factorable. And then based on the factorization, I think we're going to get a better idea of what the heck is going on here. So you should be able to factor a quadratic expression being in a calculus class, I hope. All right, and there you go. There is the correct factorization of the numerator and the denominator. So, yeah, let's analyze this a little bit. Note that this factor only occurs once in this entire rational function. So this factor only occurs once. So that's going to be an indication to us that this is really called a non-removable, well, shoot, but this dude's an R. A non-removable discontinuity, okay? A non-removable discontinuity. So there will be, at x equaling -5, an area that's discontinuous on the graph of this function, okay? Here we have two factors that repeat, which means we could cancel them out, but before we do that, we need to understand that x cannot be equal to 1. If x is equal to 1, then this whole thing is undefined, right? Because you'd have 0 in the denominator. So here's the deal. If a factor repeats on both the top and the bottom, it's called a removable discontinuity. Okay, so let's see what is going on here. We have the function, therefore, f is discontinuous where? Well, first of all, at x equals what? You set this equal to 0, solve for x, you get -5. So at x equaling -5, the function is discontinuous. Now, what are the conditions of discontinuity? Again, go to your definition, continuity, there's your 3. 1, 2, 3, okay? So in this case, because the factor x plus 5 only occurs once in the denominator, it's undefined at -5. So f of -5 does not exist. It's undefined. So condition 1 is violated. Furthermore, the limit here is not going to exist based upon it being a rational function. If you approach -5 from the left, and then if you approach -5 from the right, you're going to get a negative infinity situation, which that's not going to result in any limit. So that condition is violated. And remember, as soon as either one of the first two conditions is violated, then 3 is also violated. All right. So what about at x equaling what? Well, if x is 1 here, you get an undefined situation. So what conditions are being violated? Well, I just told you one of them. If x is 1, this is undefined. So f of 1 does not exist. So that's condition 1. F of 1 does not exist. The limit does exist. If a factor repeats on both the top and the bottom, then the limit will exist. You actually get a hole here. You actually get a hole where? This is something that we talked about in 128, but there's going to be that didn't really help. Okay. If you were to cover this up and now replace both of these x's with a 1, what do you get? 1 minus 2 is what? Let me put the 1 here. 1 minus 2 is -1. And then 1 plus 5 is 6. So you actually get a hole in the graph of the function at 1, -1/6. Okay? So actually that looks something, this isn't the graph of this function, but it looks something, that's what it's referring to. There'd be a hole there, right? So remember, the limit here did exist, okay? Doesn't matter if the function exists at this point or not. The limit as x approaches 1 does exist. So that condition, this condition number 2, was not violated. Condition number 2 is not violated. We're good there. The limit does exist. However, what did we say? If either one of the first two conditions is violated, then the third and final condition is also violated. Okay? All right. That was a tough one. There's a lot going on there. Okay, I'll go over it more as needed during our class time. All right, just a couple more examples, then we'll be finished for this section. Okay, here hopefully we can take a sigh of relief here, have a sigh of relief, because this is something that we did in 128. This should be basic stuff. This deals with the topic of domain. All right, and we should all be familiar with that topic, domain. So, let's finish up section 9.2. Find the values of x for which each function is continuous. Use interval notation, something else we should be definitely familiar with. Well, if you do not have any variable or variables occurring in the denominator, or if you do not have any radicals involved, then the domain here will be all real numbers. So, this function is continuous on the open interval from negative infinity to infinity. All real numbers. Letter B. Again, we're actually stating when the function is continuous, which is the same as determining the domain of the function. Do we have a variable or variables occurring in the denominator? Yes, we do in this case, right? So all you have to do is let the denominator really be not equal to 0, and then solve for x. So we add 8 to both sides, we divide both sides by a deuce, and we get x cannot be equal to 4, right? If x is 4, it's undefined. Okay, so how do you write down, using interval notation, when this function is continuous? Well, you just do from negative infinity all the way to 4, not including 4, or from 4, so you just jumped right over 4. There's a hole there at 4, right? Or of an asymptote, I should say, in this case, a vertical asymptote. Or from 4 to infinity. That's it. That's when the function here is continuous. All right, and finally, letter C. Well, you have a radical involved. So when you have a radical involved, you just simply let whatever that expression is under the radical be greater than or equal to 0, and then you isolate x. So let's go ahead and first subtract 7 from both sides. And then let's go ahead and divide both sides by -1. Same as multiplying both sides by -1. And what do we do with the inequality symbol? You flip it. If you ever multiply or divide by a negative to isolate the x in an inequality, you must flip the inequality symbol. So that's what we get. And then we need to again express this in interval notation form. Okay, so x is less than or equal to 7. So we're going forever to the left, that's negative infinity, all the way to 7, including 7, because the or equal to component is there. We must use a bracket to indicate that inclusiveness, that it is allowed to equal 7. All right, hope you're doing well, hope you're staying safe and having fun. We'll see you real soon.